When we were working through examples of continuity, you might have noticed that the two functions that turned out not to be continuous, they were not continuous for very different reasons. It turns out there are a few different types of ways to not be continuous. First of all, let's name the phenomenon of not being continuous. So if a function is not continuous at a particular x value, we say that that x value is a discontinuity. So a discontinuity is just a place where a function is not continuous. And there are three main types of discontinuity. So one is a removable discontinuity. And a removable discontinuity is something that looks like this. So in this, let's say our x value is a here. So remember, to check if a function is continuous or not, we have to check if the limit of the function at a is equal to the value of the function at a. So for this situation, the limit exists, and also f of a exists. But the problem is, the reason this is a discontinuity is because these two things, even though they both exist, they're both finite numbers, they aren't equal to each other. And that's what makes this a removable discontinuity. The reason it's called a removable discontinuity is because we could fix this discontinuity just by changing a single point on the graph. Right? There's another way for a discontinuity to be removable, and that's if we had a graph like this. And here's a. So in this situation, right, remember we're comparing the limit at a to the value of the function at a. So in this situation, the limit exists, but the function itself is not defined at a. Okay, so this function isn't continuous at a because it's not even defined at a, but this is still a removable discontinuity because we could make this function continuous at a just by assigning a value at this single point a, and that would make it continuous at a. So removable discontinuities are sort of the best kind of discontinuity. They're somehow the least offensive kind of discontinuity. Right, another type of discontinuity is a jump discontinuity. And a jump discontinuity is what it sounds like. It's just wherever your graph jumps from one value to another, like this. So if we're testing the definition of continuity at a jump discontinuity, what is it that fails about the definition of continuity? Well, the function itself is defined at a, so this exists. But the limit at a, right, there's a one-sided limit from the left, there's a one-sided limit from the right, so the two-sided limit does not exist. And this is because the one-sided limits either don't exist or don't agree. Right, so here's an example where the one-sided limits both exist, but they don't agree. Another way you could have a jump discontinuity is if, say, it was like this funny sine 1 over x kind of function, where it goes up and down like this forever. Right? Maybe it's like that to the right, and to the left it's like this. So here, the one-sided limit from the right doesn't even exist, and so this also counts as a jump discontinuity. Jump discontinuities are somehow worse than removable discontinuities because to fix a jump discontinuity, you can't just change a single point. We couldn't just take this single point on the graph and move it down here. It would still be discontinuous. To fix this discontinuity, we would have to sort of bend an entire chunk of the graph like this. And that's pretty drastic surgery. Right? Removable discontinuities are nice because you only have to move one point. Jump discontinuities are not so nice because you have to mess with a whole interval of the graph. The third kind of discontinuity is an infinite discontinuity, and an infinite discontinuity is like many rational functions have, so something like this. And with an infinite discontinuity, if we ask ourselves about the definition of discontinuity, or the definition of continuity, here I can even define the function at the point A. So here the function value exists, and the limit also exists, but it's plus or minus infinity, right? And if your function is defined, it can't be taking on the value infinity because that's not a real number. And so if the limit is infinity, it's never going to be, the limit is never going to be equal to the value of the function. So, so that's what makes this an infinite discontinuity. You can tell it's a good name because, hey, one of the limits is infinity. Many rational functions have infinite discontinuities. Not all of them, though, but that's a very common situation. Also, many trig functions have infinite discontinuities. Just to check on our understanding of these three different kinds of discontinuities, let's look at a graph and classify the discontinuities of this function. First of all, let's find the discontinuities of this function. Remember, a function looks continuous wherever you can sort of draw the graph without lifting up your pencil. So in this part of the graph, it's going to be continuous because we can draw this part without lifting up our pencil. It's going to be continuous for all of these x values, all the way up to -3. At -3, we have to lift up our pencils and jump down to here. So there's a discontinuity. There's a discontinuity at -3. Okay, then it is continuous again because we can draw this piece without lifting up our pencils. And then at 0, there's another discontinuity because we jump up to here. So there's a discontinuity at 0. And then there's a discontinuity over at 4. We have to lift up our pencils to skip over the x value 4. All right, so what kind of discontinuities are these? Well, at -3, you can see that the one-sided limits at -3 are clearly plus or minus infinity. So -3 is an infinite limit, infinite discontinuity. And this is because the one-sided limits are plus or minus infinity. All right, what about the discontinuity at 0? Well, at 0, it looks like the graph from the left, it's heading towards, say, -1/4, but from the right, it looks like it's heading to 0. So both one-sided limits exist, but they aren't the same. And that means that this is a jump discontinuity. So jump discontinuity because the one-sided limits exist but aren't equal. Okay, what about at x equals 4? Well, at x equals 4, there's just this hole in the graph. We could make the function continuous at 4 just by plugging the hole, just by defining the function at that single value. And that means that this is a removable discontinuity. Right, so this is a removable discontinuity because the limit as x goes to 4 exists and is finite. So we could make it continuous if we just redefine the function at this point. You can see that if you're looking at a graph, these three kinds of discontinuity are pretty straightforward to identify. Infinite discontinuities, the graph flies off vertically in one direction or the other. Jump discontinuities, it's just this jump from one height to another. And at removable discontinuities, there's just a hole in the graph. Although maybe I should point out that at this removable discontinuity, even if the function were defined up here, this would still be a removable discontinuity. We would just need to fix the discontinuity, we would just move this point down here.